won't become standard. I hope it's first few more, and then we will come back and meet in Barcelona or some other places in person. So I hope everything will come to normal, which I wish to everybody. Okay, so in this talk, as you see, there are 3 co-authors, but this talk will be based on, it will be based on 2 in some sense independent works, which have like tight connecting topics. So all started even before 2019 when I was in Vienna. We started to talk with Piotr, and at that time Paweł Potorski was PhD student, and we start discussing this Lorenz map, which are main thing in this talk. And it is how it started. And finally, Paweł made his PhD based on that topic. And now there is another one, Łukasz, who is also my PhD student, and who continue this line of research. So as I said, main topic will be Lorenz maps, expanding Lorenz maps. So these are maps on the interval, which have 2 pieces of monotonicity. There is critical point, and usually because of this critical point, some problems arise, and I will try to show you why the problems come to when studying dynamics of these maps. But in classical way, you require what you have on that slide. So critical point, almost everywhere differentiability, except maybe finite set of points, and everywhere slope is larger than 1. So it's like quite steep graph. So it more or less looks like on that left picture. And of course, it doesn't have to be like that, but in most of talk, I will stick with maps which are piecewise monotone. So that will help to understand the dynamics, but in fact, it won't be that easy as you may think. Even if the slope is constant, many interesting things can happen. Okay, so a little bit about motivation, how it came to the literature. So it was born because of studies of Lorenz attractor. So people wanted to understand Lorenz attractor. And then in the original Lorenz attractor, they observed that if you like take nice Poincare section, you can generate interval map. And here is what you get if you use so-called geometric model of Lorenz attractor, which, as far as I know, starts with works of Guggenheimer, but then many people try to analyze this, try to analyze this model. And here you have, in this smaller square, you have what I was calling Lorenz map, right? So you have 2 pieces of monotonicity and critical points, and this critical point, it comes here from this trajectory. So in fact, for Poincare map, it may be undefined because this point never comes back. But for us, there will be some value assigned. All right. So one way of looking at those maps is just you take map from interval 0,1 to 0,2, and you make modulo 1, and that way you get somewhere this critical point. And of course, you should also keep differentiability. So sometimes looking at that map F, it may help you to look what's going on with the dynamics. And if I use this modulo 1, then I automatically assume that in critical point, the value is 0. But of course, I can put it 1, or it's my choice. And sometimes you will see it later. It really makes things harder if trajectories pass through this point C. And it may lead to some confusion or some mistakes, even if you don't take enough care about what's going on with point C and how it is mapped. Okay, so that map on interval is discontinuous, but you can use standard technique of blowing up orbits like you have in Don Juan extension, and then you can move everything from interval to Cantor set. So simply you take C, put hole there, and then just take pre-images and propagate these holes through the whole interval. And because this map is expanding, these pre-images will fill densely the whole interval, and that way you will get Cantor set. So you can do it like in Don Juan, or you sometimes maybe it's better to, and that comes from, I learned this from paper by Piotr. So what you do, you just take natural ordering of points on the interval. So if they are not in the same hole, you just look where they are on the interval, and you can compare. And if they are in endpoints of hole, then you just take left and right, and you have order on. Now, before you introduce metric, it's not maybe Cantor set, but on that set, that interval with holes. But then if you do something like this, so simply you take these 2 points with the relation, and you take the first hole that falls in between them, and then you take the distance on the interval, which can be 0, and then the number of the hole. And that way, if you do it that way, so it's not like exactly geometric summing up intervals, but it also defines Cantor set. So this procedure is well defined, and it gives you compact space, which is Cantor set, and you can deal now with your dynamical system. If you pass from that map on the interval, if you pass to Cantor set, you have standard dynamical system, so continuous map on Cantor set, and you can look on all topological properties that you have in topological dynamics. But sometimes maybe it's better or easier to look on that Cantor set, but in many papers people don't do that. They rather look what's on the interval and look at what one-sided limits, and try to say something like they don't exactly go to Cantor set, but they treat the dynamics like it happening on Cantor set. And as I said, sometimes it can be misleading. I will show you examples later. Yeah, and of course, you can speak about transitivity, mixing, other notions like entropy, because you have system on Cantor set, so everything is perfectly defined. And there are also these characterizations for some cases, like here is the paper I like very much by Jerome Buzzi, which characterize mixing in beta transformations. So now this alpha here is 0, and I look at these maps, and all the time I get mixing and sometimes specification, but for many parameters there is no specification. For many it is, and it's not that clear why sometimes it appears, sometimes it doesn't, despite the map looks all the time the same, only the slope is changing. Yeah, but it gives hope that maybe in these maps mixing will be common if you know that result. Okay, and that was the first question that we started with Peter and Pavel. So we were asking, okay, when in these Lorenz maps with constant slope, for like, maybe it's better to stick with that. So let's think that we have constant slope. So when in that maps we have mixing, and at start we looked at approach that was proposed by Hofbauer also many years ago. So he built something which is similar to symbolic dynamics. So he takes natural partition of this interval, splitting into critical point, and then he iterates these sites, let's call them sites, and intersect with Z and looks what set you obtain. And that way he constructs kind of diagram. So he just iterate, intersect, iterate, so get kind of partition each time, and then he draw arrow if one of the sets is the image of the other. So that way he gets kind of graph, infinite graph, because there can appear many different intervals after these intersections, because you don't know exactly where this C goes, so it can cut the space very much. And he called this Markov diagram. And what was observed by Hofbauer, and we were using this in simplified form for Lorenz maps, because Hofbauer was doing this for as many pieces of monotonicity as you wish. For us, it was enough to have 2 of them. So what he observed is that sufficient condition for transitivity is similar to what you have in symbolic dynamics. So you simply have to find like subgraph such that elements on some vertices cover the space. So like get some partition of the space by element in my diagram, and then if it has structure that I can go between any 2 elements without going out for my sub diagram, then I have transitivity as long as I have this covering here. So this was Hofbauer's result, and then because it looks very similar what you have for shifts of finite type, so it's not hard to imagine what we thought. Simply the first impression is, okay, so let's look what are conditions for shifts of finite type for mixing and try to apply them here. And here you have condition which is completely analogous for what you have for shifts of finite type. So if you have this diagram which gives you transitivity, then look there for cycles. And if lengths of these cycles are coprime, if you can find such lengths, then you have mixing. Okay, so this is exactly the condition for shifts of finite type. It's very analogous, despite the diagram is different. So the same very similar argument works. Yeah, important thing here that you should start and finish in the same vertex. So not only find these cycles, but you have to attach them in one vertex. And this is useful. So it doesn't, this property, we were using this a lot, so it doesn't apply for any vertex, but if you can go from some vertex to vertex from this to this like basic partition, then you can make cutting. I will show you this on a diagram in a moment. So this will be maybe more visible how this works in practice. Okay, so it's like here. So this is one particular example of this diagram of Hofbauer. So what we have here. So here we can find a path of length p from some vertex to this basic one, and this is subset of it. Then by this lemma tells us that here is also cycle of length p, and the same here. Like we have a path from this A to 0C in Q steps, then we have also a path from 0C in Q steps. Yeah, so this diagram, it's written here when it works, in which cases, because it's kind of, so in the proof we're just building general diagrams, and it was very much based on previous works of Piotr, who analyzed these graphs. So in that particular case, what you see here, you have path of length p plus 2. It's here, like here 2 steps and p. But as I said, by lemma, we have also here cycle of length on length p, and again we have path of length q plus 3, and also here cycle of length q. So we have numbers of cycles, of lengths of cycles from 0c, which is p plus 2, q plus 3. So these are coprime, of course, and that way we know if I have map which have this diagram here, then I have mixing. And here you have one of the cases. So we were analyzing several cases to find out where this mixing can appear. And this is one of special cases. So if you look at that map, square root of 2 plus this fraction here, so that map. So if you look at graph of second iterate, you can see here invariant region. So definitely that map is not mixing because it like permutes this interval in the center in splits in one iteration to left and right, and then it connects again. So definitely you don't have mixing, but that map is transitive. So this is example that not every transitive Lorenz map is mixing, but as you will see in a moment, it's quite unique situation. All right, so that picture, it's parameter space from works of Piotr. So this Raith and Stachelberger paper, and here this white triangle is where they analyze the situation, and this light gray shows where there is no transitivity. And that example that I show you, this is this red dot which is in top of this gray region. And this is not by accident. So later I will show you theorem which tells you more. Okay, but it is what we observe that here is this one bad case, and in fact there will be two more on this baseline. Okay, so that's what you see on that picture. This was analyzed by this Hofbauer's approach by Piotr in several papers. Okay, that one I won't speak. But then there is also quite of literature using different approach, and it starts with papers of Glendinning, but there are many others. So Glendinning and Sparrow, and some of these approaches referred to in PhD thesis of Palmer. Some other people were speaking about it. So what's the approach? So here you have like essence of what is in Glendinning paper. So if you look at that paper from 90s, you will find this picture. Okay, so this is like complete triangle. In case of Peter, it was finishing somewhere here in the middle at cube root of 2. So here you have much more. If you look at it and you say, wow, that's everything is analyzed. So how they get that? And it is using quite nice observation. So to draw this picture, Glendinning was introducing something which he calls primary NK cycles. So he was looking for some special type of cycles. So here I have n elements. They are ordered like this. C is between z and k, and z and k plus 1, n minus k plus 1. And so this is ordering. C is here, and there you have additional requirements. So this z, they form periodic orbit. On this orbit, you jump by k in k positions to the right. So z1 to zk plus 1 and so on, and you make it cyclically. These numbers k and n are coprime, and you also require that image of 1 and image of 0 is in proper position. So this is it. So this primary NK cycle is like special periodic orbit that you may have in your system. And then in this paper, if you look, you have, it seems, full characterization of transitivity, because it says that it says here beta transformation, but these are these Lorenz maps with constant slope. So it says they are transitive or non-transitive in then only if you can find this primary NK cycle. So it seems like everything is characterized, right? Like transitivity have full characterization by this NK cycle. So this was big surprise when we learned about this result. But the problem with this result is that it is what written in this paper. So it says, okay, if you want topological proof, look into another paper of Glendinning, but it was never published, so we don't know what's there. Or look, this 13 is this thesis of Palmer, but in fact, this is not about transitivity. This is about ergodic theory. So and it's stated differently. So this is not that tight connection and not that easy to figure out if there really is proof of that theorem or not. All right. So just like maybe to digest it. So it says, okay, transitivity or lack of transitivity means exactly that I cannot find this primary NK cycle. But then let's come back to that example that I show you, which was transitive, because what Piotr proved is that it was in his first paper. If you have square root of 2 as this leading coefficient, or beta is greater or equal square root of 2, then you have always transitivity. Okay, but if you look at that particular, so also in proof, this is particular case. This is like special case that you need some different argument proving transitivity. But if you look at it and just compute, then you can find 2 points which are on different sides of C, which go in cycle. And images of 0 and 1, they exactly hit these points. Okay, so let me just come back. Right, so it was telling, okay, so if there are 2, they just have to be periodic orbit. It will be N1 cycle, so numbers definitely coprime, and here we will have equality, so everything is satisfied. But this map is transitive. Okay, so it shows that there is something wrong with this theorem. And then it is what we observed, that if you have this primary NK cycle, then what happens that if 0 and 1 go to, so exactly that happens when on what was in the previous example, then you don't have transitivity. Then you have transitivity, but you don't have mixing. And if one of these inequalities is strict, then you don't have transitivity. Okay, so at least for one direction, for proof in one direction, what was in Glendinning, it was okay, except that special case where you are on the top of this region. And we didn't check the proof if it is if and only if. So it's maybe in Palmer's proof, and maybe it's just adopting it will work, but we never check it. So at the moment, it's not 100% sure that this is still if and only if condition, but for sure finding this cycle is enough. Okay, and then Pavel spent some time, and because in Glendinning there were like recursive formulas for finding these regions. We tried to find like direct formulas, but only for small parameters. It was possible, but not in general. Okay, so that is how this looks like. And in like tops of all that regions, everywhere here, it's exactly the case when you have transitivity but not mixing, and inside of these regions you don't have transitivity. So it is what I said for Piotr. The picture was finishing here on that third root of 2. So these were 2 dots at the bottom, and that one dot which I drew you before, where there was no mixing but was transitivity. And lack of transitivity in that triangle was here. Okay, so that was the first thing we were working. And then we were also interested in renormalization. And in that work with Piotr and Paweł, we were looking for some strong version of transitivity, which is called L.e.o. So most of you probably heard about this property in case of interval maps. And yeah, so now is the question how to define it. So originally it was defined like here. And it's slightly different what you know for interval, because for standard approach of interval dynamics, you simply require that open set grow to the whole interval. That's locally eventually onto as it is usually defined. In that case of Lorenz maps, it was defined differently. So it was saying that in every open set or open interval, you can find 2 intervals that after some iterations, if you restrict some iteration of that map to that interval, then you will get one of these basic pieces. All right. So look at this definition in the bottom. So we introduce it in our paper, and at first look, it may look artificial. So what we add here, we want this homeomorphic image, but we also want that a continuity don't break in meantime. So when we iterate this J, we on in each iteration want to have map continuous, not only at the end, because what can happen is that you have your interval, then you iterate it, then it breaks into 2 pieces, they travel independently somehow, and then they glue properly again, and you get your homeomorphism. So that extended definition, which we call strongly L.e.o, it doesn't allow this situation, and that definition of Glendinning and Sparrow, so it was in 2 papers, it appeared in 2 papers, it allows that. So this interval can break, passing through critical point, and then somehow synchronize some matching at the end happens, and they are back together, and you have homeomorphism. All right. And why we did it, why we extended this definition? Because again, in papers of Glendinning, there was a theorem which says that we have this locally eventually onto exactly when there is this STR condition. So either one of endpoints is fixed or one of endpoints go to critical point, or the map doesn't admit renormalization. So that was like looking like full characterization. And then we found map which distinguish these 2 properties, this strong L.e.o, where we want in every iteration continuity and then homeomorphic image, and the situation when we only look what's at the end. So these are like just to show you that we just calculated exactly this map. So its graph, it looks like this. Okay, let me also look here. So what we were able to prove about that map, so this map has renormalization, and we can just exactly provide the formula for renormalization. But this map satisfies this definition of Glendinning. So in every open set, I can find two intervals that after some iteration, they will go to left or right interval in homeomorphic way. But what will happen that continuity will break in the middle. Yeah, and we spent some time proving this, so that's not, if you look at the graph, then it is not that obvious that it will happen, but we prove it that it's exactly the case. That this interval have to break before it comes to final position, and it is how this renormalization looks like. So this is mapped like this. Yes, so in fact, what we are also able to prove is that if we extend this definition to this stronger form, then it gives you equivalent condition. So lack of renormalization, or the special form when 0 or 1 are fixed or go to critical point, this fully characterize this stronger condition. So yeah, and it was with hard work, so we have to work a little bit to prove it. All right. Yeah, and here you have another example. It's maybe not that well visible, but it is example. It is example that that we have mixing, but this map is not L.e.o, and yeah, again it involves some arguments to prove it. But for that map, because of this slope, we know that for sure it's mixing, because we know every map with this slope is mixing. But with, again, here is sketch of argument, but maybe I won't go into that. So you can prove that this condition from L.e.o cannot happen. Yeah, so mixing is like more general, and so far we don't have like nice characterizations saying which among mixing maps are these L.e.o, that we don't have. Well, we didn't also spend that much time on that, but still it seems like interesting, because we have, like, it seems complete regions where there is transitivity and lack of transitivity. We have complete regions where there is mixing, so it would be maybe nice to know where you have the strongest mixing condition, this locally eventually onto in one of the versions. All right. And now we slowly coming to the part of research that we were doing together with Łukasz. So this is more recent part, and it's related to something that in the literature is called completely invariant. So I have my Lorenz map, and then I look for set that is forward and backward invariant. Okay, and this is one comment which I mentioned at start, that if I have critical point, then because of expanding condition, these pre-images will be dense. So if I'm able to find closed, completely invariant set, which is not the whole space, so proper subset, then it cannot contain critical point, because otherwise it will be everything. Okay, and yeah, so this is also what we were able to prove with Łukasz. So if you have transitivity, then not only critical point, but every point in this extended Cantor set will generate you backwards then set. So in fact, for this case, you cannot find proper completely invariant subsets. If you have transitivity, you will never find closed proper invariant subset, which is completely invariant. So this type of set, they may appear only in case where there is no transitivity. All right. So the inspiration for this, for looking at this set, was this theorem by Ding, which is quite interesting. So what this theorem says, at one direction, it tells you that if you are able to find completely invariant closed subset, and then if you like calculate these numbers, this E minus, E plus, then take these intervals and check where they hit C. So this N tells you the first iteration that C is inside. So L and R tells you the first moment that this interval E minus C will cover C, and right is the same, but for the right side. Then if you define your map that way, then you will get renormalization. Okay, so this is the first part of this theorem. And second part tells you that you should be able to work conversely. So if you have renormalization, then you should be able to find set B, which is completely invariant and closed, and it will give you your renormalization. Yeah, so I start with renormalization, and then I'm able to find set for which if I define map that way with all that procedure, then I will get my renormalization. Okay, so let us come back to that example that we have with Piotr and Pavel. So of course it was for different reason, it was made for different reason, but for this map was this locally eventually onto, so it was definitely transitive. So it doesn't have, by this argument I showed you a moment ago, it doesn't have proper closed completely invariant subsets, but on the other hand, it has renormalization, which we were also able to write down. So if you have this example at hand and you look at this theorem, then you see that this second part, it cannot be true, right? Because we have exact example. We have renormalization, but there is no such B that can give you that map. Okay, so it means that some work is maybe needed. Maybe something can be saved from that theorem because it looks really nice, and this part looks good, works good. So there is problem with this like opposite. We will spend some time thinking what you can get. All right, and this is how this machinery in Ding was working, or how he was trying to prove it. So he was just defining set Fs, which, so simply he had this renormalization on some interval uv, and then he was looking on points which eventually fall inside uv, but without boundary, and was collecting this in Fs, and was saying that this set is always open invariant. And then that way he was defining JS, which should be that set used for defining this renormalization. That was like very sketchy idea of the proof, what he was trying to do. So the first step was looking at that set. So of course it will be open, but the problem is if it's invariant. And yeah, so what we observed, that problem was with this claim about invariance, because it sometimes is not invariant, and all depends how endpoints of this interval of renormalization, how they behave. If they behave badly, like here, that they don't enter to the interior, which may happen, then you don't have complete invariance, and then everything fails. Yeah, so unfortunately sometimes it may happen. Yeah, but on the other hand, what we observed with Łukasz is that if you have this primary NK cycle, then you will always find renormalization, which is given by length of this cycle. So this is one thing. If you find another one, and these numbers L and R here, if at least one of them is greater than n, then both are multiples of n. So if I find another renormalization with at least one of these numbers bigger, then it will be multiples of n. However, if the cycle is this boundary example, that boundary case that I was showing you, if it's on the boundary of the region, then Fs won't be completely invariant. But if these are other cases, then that what was in Ding, it works. So so this sets.js will be good, and it will give you back that renormalization, that one which we found. Okay, so this Tn. If this cycle was nice in the sense that 0 and 1 was not hitting this periodic orbit, then renormalization will be characterized by this completely invariant subset. But what can happen is that sometimes, so also Ding was hoping that you will that this renormalization, if you have this cycle, the renormalization will be minimal one in the sense that all others will be multiply of these numbers, but of these numbers, like in our case, I have renormalization 5, 5, so another one should be like multiply of these numbers, but then we were able to find example which has here it has primary 5-2 cycle, so it's not transitive. It has that special renormalization with T5, T5, but there is another one which both numbers smaller. So sometimes it may happen that that one is not like in sense minimal, or in some sense independent of the other renormalization that you can find in your system. On the other hand, and maybe I won't go into that, but I will show you this example just to finish slowly. So that example before, it was showing that renormalization from NK cycles, if you get it, maybe it's not the minimal one. Here in this example, it is minimal one because there are other two renormalizations, but with bigger powers of the map. But what happens here is that if I try to recover or find these sets that gives me the renormalizations, then for this one and for that one, so for S and S hat, I will find proper closed invariant set that will recover my renormalization, like in theorem of Ding, but for that one I won't find it. So in some sense, this S bar, it will be invisible in terms of these completely invariant sets, and we also not understand the mechanism or where this can break, like how many of these, because for sure, if you have constant slope, then for sure you have finite number of renormalizations. It must stop at some point, because after each renormalization, slope increase and it cannot go above 2. So you have finite number of them, but for us at the moment it's not completely clear why sometimes you can find these completely invariant sets and find your renormalization, and why sometimes you cannot. Except of course we know what are the conditions, but like having big picture, why sometimes it happens, why sometimes it doesn't happen, it's at the moment, we don't see big picture. We know some examples, we know why it happens, we know what are the conditions, but like saying in which maps the situation will happen, in which non-transitive maps the situation will happen, in which it won't, it's quite unclear at the moment. Okay, so it is in brief what we are doing with Paweł and Łukasz. Łukasz is now working on further topics from this, and I hope not long from now he will finish his PhD. So it will be something related to that topics. Okay, and maybe that's a good moment to stop. So thank you very much for your attention.
Okay, Piotr, nice